All right, in this problem, we're going to do another boom chain problem, but this one is a little more complicated. It's kind of the problem that most students don't really like to do because we're going to say that the boom actually has mass. If the boom has no mass, then we can add these three vectors all together in a nice triangle, and it makes it easy. But in this one, we're going to say that there's a 2,000 Newton force weight hanging off the end of this boom, but the boom itself is uniform mass, and therefore there's a 1,000 Newton weight of the boom, which would be right in the center. If this wasn't uniform, we'd have to actually put this weight like somewhere else, but this is uniform, so we're going to put a 1,000 Newton weight right in the center. We have a certain setup here with angles in here, so we can kind of figure out a couple other angles here. We have this angle up here would be 40 degrees if we need that. This is 65, so that means this angle right in here would also be 65, and this angle here would also be 65, like so. Okay, so what we need to do here is we need to do this in the kind of the parallel force type of problem. We need to normally the wall would be exhibiting a force directly straight along the boom this way. That is, if this boom does not have any mass whatsoever. But this does have some mass, so it's going to kind of pull the boom down this way, but also kind of down this way. So we're going to end up with a force kind of coming up at an angle here, not directly along the boom, but kind of at an angle to the boom. The wall is going to be pushing up a little bit on this boom. And we need to figure out what the force is here at this place. So what we're going to do is we're going to use this this place right here, because remember we have a force pulling up this way, and we have a force pulling down this way, and now we have a force pulling down this way, of course. We need to figure out, we're going to measure from this location right here and do our, try to do parallel forces problem. So what we want to do is these two forces and this force, we need to all resolve into perpendiculars and parallels to the boom. So if we do that, let's try to draw in some lines here. I'm going to draw a vertical here like that, and another vertical here, and another vertical that would come up like that. And then we'd have parallels. One would be coming down like this, one would be coming down like this, one would be coming down like this. And we could put on, this is going down, whoops, let me switch here. This would be going down like this, and this would be coming down this way. This would be coming this way and this way. This one would be going up and over like this. And we can put in our angles here. If this was 75 right here, then this angle right in here is going to be 15. If I can draw that in nice. And then these angles right here, this angle here would be 25. And this angle here also would be 25. And so what we want to do is we want to figure out our torques here. So, and measuring from this point right here. So if I could go to here times this plus here times this, those would be clockwise torques. So under clockwise, I'm going to have whatever this force is times 1/2. So we need to figure out these components here first. So if I look at this one right there, that would be the hypotenuse times the cosine of 25. That's the adjacent one there. So that would be 1,000 times the cosine of 25. And that force is, if you do that, 1,000 times cosine of 25 would be 906 newtons. This side right here would be 1,000 times the sine of 25, and that will be 423. You should check these for me. This side right here would be 2,000 times the cosine of 25, which is 1830. 13. And this side right here would be 2,000 times the sine of 25, which would be 845. Okay, and we don't know this one up here. So now we know we have clockwise torques. We're going to have 906 times 0.5. So we're going to do 906 times 0.5 plus 1813 times 1. So these are going to be our clockwise torques. That should equal our counterclockwise torques, and the only one we have is this one going up this way at 1 across. So we can label this thing here, we'll call this the chain perpendicular force. So this force is going to be our counterclockwise torque. So we're going to have these equal, and we're going to actually then be able to calculate this and figure out what this this perpendicular force would be. And if we do this math on this, we should get 2266 newtons. So now we know what this is right here. Well, one of the things we want to do is figure out what is the force in this chain right here, as we did like in the last problem. And of course, this angle is 15. So the chain here should equal the 2266 over the cosine of 15. Hopefully that makes sense. If we take the cosine of 15 right here, that'd be the adjacent, which is what we know, over the hypotenuse, which is what the chain is. So the hypotenuse would actually be 2266 over the cosine of 15. So that gives us a chain, this force right here, a chain force of 2346 newtons. And you should always pause this video and make sure everything's working out right. So this chain would be 2346. So now we have the chain. That's one of the first things we need to do in these kinds of a problem. And the other thing we need to do then is figure out, what kind of force do we have working up here along the boom? Well, we have a force working down this way of 845, a force working down this way of 423. What's this force up here? If we could figure that out, that would be nice. Well, the chain is 2346. So this side over here is the opposite side, so it should be 2346 times the sine of 15. 2346 times the sine of 15. And if we do that, we get a force of 607 newtons. So we have a total 3 forces right here, 845, 607, and 423, and those are all to the left forces. And if I add those all up, I get 1875 newtons, which means I'm going to need 1875 newtons to the right. I'm going to need that to balance that out. So I'm going to add that right here, going straight into the boom. That would be 1875. That has to balance out all 3 of these things going to the left. Now what I want to do is I want to look at my ups and my downs, and you'll see that I have, if I have ups and I have downs, I have an up right here of 2266. 2266. I have a down here of 1813. And I have a down here of 906. And you'll see that if you add these downs together, that'll be more than your ups, which means we need another up. And if you add these together and subtract out this up, you will see that we still need 453 up. We need 453 up. So what we're going to do is we're going to take that 453 up and we're going to put it up right here. That's going to be 453. And so what can happen is we have an up and an over to the right, and we can take those 2 vectors, add them together to get a resultant vector right here, which is what I'm trying to figure out how the wall pushes on this boom. And so if I take 1875 squared, 1875 squared plus 453 squared, and then I take the square root of that whole thing, I will get a resultant vector of 1929 newtons, if I've done my math right, and you should check me on that. So my resultant force that's going to be on the wall acting on the boom is going to be 1929 newtons, but you'll notice it's not working straight down along the boom. The reason is because we have the weight, this boom has some weight here in the middle. If this boom was negligible mass, had no mass, we would have just a weight, the force working directly along the boom. But since there is a mass to the boom, we're going to be coming here at an angle, and we can try to figure out what that angle is right in here. And that angle, of course, would be opposite over adjacent, so I'm going to use tangent. Tangent of the angle would equal 453 over 1875. And if I divide that and I do the inverse tangent, I'll see that this angle in here is about 13.6 degrees. So I'm going to be going at 13.6 degrees below the boom. Instead of going directly along the boom, I'm going to come up underneath the boom at an angle of like 13.6 degrees. So that's how you do a boom chain problem if the boom actually has mass. You're always going to start from this fulcrum point here. You're going to measure out torques so that you can figure out what this force is here. You'll use this force to figure out the chain force. Once you have all these left forces, you'll know that that's how much right force you'll need. And if you add your down forces and subtract this up force, you'll know how much more up force you need, and you'll be able to get a resultant vector there. Hope that makes sense. I know those problems are a little bit difficult, but if you watch that, I think it'll help you with your lab question.